My name is Michael Affenzeller. I'm chairing today's keynotes on behalf of Francesco Longo, who had a short-term arrangement and clashes in dates therefore. And it is my pleasure to announce our first speaker, Professor Giancarlo Fortino, who is full professor of computer engineering at the Department of Informatics at the University of Calabria. Professor Fortino has a very high academic recognition and impact, which is not only shown in his age index of 52, but also very high reputation, which you can see in the number of program chair activities, which is around 500 over the years, and many duties in organizing conferences and editing journals special issues. The topic of today's talk of Professor Fortino will be Agents Meet the Internet of Things towards cognitive and interoperable ecosystems of networked smart objects. Please, Giancarlo, the stage is yours.
Thanks a lot for your nice introduction. So I will share my screen and my presentation. Okay, I hope you can see my screen, right? Okay.
Yeah, it's fine. Yeah.
Okay, so the talk of today is related to our research activity on the integration of multi-agent system with Internet of Things in order to analyze, design, and develop, let's say, new, smart, even cognitive IoT ecosystems. So let's start from some very basic definitions, in the sense that, you know, Internet of Things was established, at least the term, many years ago, but currently IoT is not yet fully deployed. So it has a lot of potential, even from commercial viewpoint, but indeed, you know, IoT again was not deployed in a dense way. So if you know, if you consider that when you walk in a street and then you wonder how many IoT devices are there, you know, the answer is maybe none. I mean, maybe you don't have any IoT devices, or even you could have some devices that could support some basic IoT task, but indeed the density of such devices is very low nowadays. Okay, so my talk is in this direction. It envisions a world in which IoT devices under different forms are dense and live with us, live with humans, and indeed they will be orders of magnitudes more than humans. Okay, so this is the outline of the presentation. First of all, I will give you some definitions, because currently there are not standard definition in the IoT realm. Then I will focus on our proposal, that is how to integrate agents with IoT, and then we worked a lot on this, and then we provided a new methodology called EcosoMet. I will show you an application of such methodologies, and then, you know, I will conclude the talk with some future challenges. Okay, let's start from a definition of IoT that is, you know, it is not a standard one, but it comes from the telecommunication world, and not from, let's say, the systems engineering world or the computer science world. So Internet of Things is seen as a network, a worldwide network of interconnected objects. Usually such objects are not homogeneous, but heterogeneous, massively heterogeneous. They could be sensors, actuators, smart devices, embedded computers, smart objects, and so on and so forth. But it's important that they should be uniquely addressable based on standard communication protocols. You know, this is a very telecommunication-oriented vision of Internet of Things. And of course, everything will be, networked, could be discovered, and then used in order to ask for services at different level, of the service stack. Another important point is the concept of smart object. This, the very first inception of this concept was many years ago, and usually a smart object is defined as a real-world object with embedded capabilities like, communication, computation, sensing, actuation, but specifically smartness. Okay, so the object could be able to be proactive instead of being just reactive to some, user request. And Internet of Things is, let's say, at the very beginning it was a kind of hype. Now it is shaping, let's say, in a direction that is something that we will meet in our daily life in the very near future. Okay, already we are in the year 2020. We got already 50 billions of devices scattered around the world. Very likely such devices are not used by so many people, but anyway, they are in our environment. They are in experimental testbed, and they're being to be introduced. Okay, think about wearable devices. Okay, many people is buying some Fitbit or some smartwatch or something like that. So it means that, IoT is coming. That's my point. But IoT is already a reality in different industry domain, like, automotive, consumer electronics, healthcare, utilities, and then you can see that already there is a good market there. Okay, a good market, and many vendors, many big players, let's say many giants, are being focused on entering in this market. Then there is another consideration, because now we are at the very inception of the Internet of Things from a commercial viewpoint. And then, of course, the focus seems to be on the device, okay? In my opinion, the devices are just objects, okay? The real value of Internet of Things will not be the devices, but the real value will be the services. So the real drivers of Internet of Things will be the services. So this is something that you need to consider, you need to reflect on. And okay, I'd like to use this definition of Internet of Things because it is, in my opinion, the correct definition. That doesn't come from the telecommunication world, but from the computer engineering, systems engineering world. Because, IoT is not a network, will not be a network. IoT will be a system of systems, okay? And this is the definition, a loosely coupled decentralized system of cooperating smart objects. And, cooperating smart objects will be systems themselves, even systems of systems, okay? So, a smart object is an autonomous physical digital object augmented with sensing, actuating, processing, storing, and networking capabilities. So this is the definition, even though it is not a standard one. There are several standardization efforts currently, in the world, in the industry world. One driven by IEEE, another one driven by AIoT, that is a European association. But anyway, we don't have yet well-established standards in this direction. And then, of course, we can have our own definition. And according to this definition, smart object could be able, to be autonomous, could be able to cooperate with each other, could be able to cooperate with humans, with other ICT systems in order to fulfill their goal. And of course, in order to do so, we need to define an architecture for a smart object involving communication, involving augmentation devices, think about sensors and actuators. And then they need to give physical services because they are real objects, okay? So they give physical services as well as cyber services. And of course, if they need to be smart, they need to have some, let's say, brain. So they need to do some decision making that is then supported by processing units and knowledge base. And of course, you can create a smart object ecosystem, putting together set of smart objects in the same domain, but also inter-domains. It means that smart objects need to be also interoperable and be able to interact not just in the same domain, but in different domains. And this is usually reference layered architecture for a smart object-oriented IoT. You see at the base a smart object, whatever smart object you'd like to think about, you'd like to construct, from a very small one, a smart pen, to a huge one. Think about the Golden Gate Bridge in San Francisco, in California. And of course, you need an internet working substratum that is not the current internet. Very likely it will be the next generation internet, okay? But anyway, you could reuse existing network infrastructure at different levels in order to make interact, make live, let's say, on the network different smart objects. And the third layer is fundamental, middleware. Without middleware, we'll not be able to manage smart object. So you need a naming facility. You need to be able to discover smart object. You need to be able to, let's say, establish a high-level interaction, not just sending and receiving of packets, but some kind of coordination based on specific coordination models. And of course, the last one, let's say the top one, is related to applications. So whatever application you'd like to develop, okay, from smart city to smart factories and so on and so forth. And the system scales, in my opinion, are important because you need to categorize the smart objects, and then you need basically two scales, two dimensions. One is the physical dimension, so small scale, medium scale, large scale, and the other one is also fundamental, that is related to the density. Okay, so currently we are able to create smart objects of different dimensions, but one of the point is how many smart objects are we able to put, in the same area, in the same context? This is something that project ourselves beyond the 5G, because, also 5G got limits, okay? So we are just thinking about, and we are working on 6G, so 6th generation, that is, an intermixing of different telecommunication technology, but also computer technologies, in order to increase the density of objects in the same area. And what's the state of the art in this context? Okay, the state of the art related to middleware is very well explored, I would say. So we passed from a very first generation of smart object frameworks in which, they didn't use any IoT term, much more focused on ambient intelligence, okay? We passed from this first generation to the second one, in which, we also delivered different frameworks with different characteristics in order to model and then implement a smart object-based system. Till, to the third, let's say, the third generation, in which we got full-fledged platforms based on devices, networks, middleware, application, and data. So everything integrated in order to provide diversified services through the vision of IoT based on smart objects. And of course, here in this yellow highlighted reference, you can find in details comparison of currently available frameworks. But what are the requirements for IoT systems? You usually get two levels of requirements. One called the system level, the second one called the things level. So usually the system level is very similar to requirements of decentralized systems, okay? Large scale distributed systems. The second one is specific to Internet of Things, involving the things level. So heterogeneity, interoperability of devices, augmentation variation, so the capability to make them evolve from the hardware perspective, how to manage such massive set of decentralized devices. Think about that according to some, projections. In 2050, we will have trillions of devices. It means that we need to have a fully decentralized management facility in order to, or facilities, in order to deal with trillions of objects, okay? And of course, dynamic evolution from smartness viewpoint, how to make evolve the software of such things, because we cannot think to manage them from a central point, okay? We need to provide them with autonomy, with smartness. And this is the point of, our research. Agents meet the IoT. Why agents? Okay, as I told you, if you know agents, because, agents was a paradigm established many years ago, almost 30 years ago. Then it evolved from 90s till the first decade of 2000, creating, I would like to say, a huge body of knowledge, okay, integrating two areas like artificial intelligence, distributed computing, and software engineering, okay? So it is now, a mainstream paradigm, even though was not applied so much in the industry domain, even though, the most famous framework to build multi-agent system, that is JADE, was developed at the Telecom Italia lab, formerly named XELT, okay, in Turin, in Italy. So it is also an industry object, not just research. And, multi-agent systems are pretty similar to the smart object-oriented vision of IoT. And here you can see the main characteristics of agents, like autonomy, social ability, responsiveness, proactiveness, mobility. These are all characteristics of agents, and they are all characteristics of smart objects. So this, let's say, this wedding was, let's say, prepared, and then we just used the multi-agent system paradigm in order to model the Internet of Things. And the very first product of our research was a middleware fully based on multi-agent system, able to model and able to, let's say, wrap smart objects under the form of agents. Here you can find, in this website, you can find more information about our middleware. Our middleware is currently based on JADE, because JADE, again, is a very well diffused agent-based platform. on different versions of Jade, able to run on different devices, from smartphone to traditional computer systems, even onto the cloud, but also into tiny devices like, you know, Sunspot, or even some very tiny sensor node based on TinyOS, for example. And this is the architecture. You see at the top the high-level smart object architecture that we defined according to some standard, or better still, some initiative that very likely will become in the future a possible standard. Then this is the platform level in which we are able to use many different devices of different computation capabilities and even dimensions. So you can see different computers, but you also got different sensor platforms, from TinyOS sensor platform to C sensor platforms to Java-based sensor platforms. And of course, I will not go into details, but this is the whole architecture of the middleware, okay? The whole architecture based on Jade. An important component is the smart object discovery, okay? I'd like just to tell you that, please, consider the smart object discovery, that this will be fundamental for the construction, for the dynamic construction, even on demand, of IoT systems. And of course, we also provided a methodology, because again, when the complexity increases, of course, you need to deal, you need to address your system using a methodology. And then the methodology involves a process, and then involves phases. In our case, the main phases are analysis, design, implementation. But the approach we proposed, that is very well documented in this IEEE transactions paper, is based on a meta-modeling approach, in which, after defining a process, we defined a meta-model for each stage of the process, and then each meta-model could be instantiated, supported by tool, in order to obtain different system models at different stage of the process, and then of the engineering of the system. Okay, so this approach is able to grant also semi-automatic transformation from the analysis down to the implementation. So this is something that is very well known as MDE concept, so model-driven engineering approach. And using this approach, we developed different use cases. We developed the use cases called Smart Unical System, another one that is related to Smart City, another one that is even related to Smart City, but from a different perspective, let's say a Smart Lighting System. So these are all testbeds that we developed in our cities, in the cities, you know, close to our universities. Of course, we also collaborated with many research groups worldwide, and then we were able also to provide contribution in other use cases developed all around the world, from the US to Australia, passing through you know, Europe and China. But anyway, these, in my opinion, are something that we constructed pretty close to us, and we provided a fundamental let's say, contribution. And just to be very quick, you know, this is our university. You see the green road. It is not a road, it's our bridge that is 1.5 kilometers long, okay? And then we created several services in order to have a smart university. So the bridge is able to be monitored, specifically the vibration are monitored, the vibration on the bridge. Then the departments could be monitored from an indoor environmental viewpoint, and also the laboratories. So we are able to monitor not only the environment, but also people using some wearable sensors. And for example, this is just a snapshot. I will not go into details of the application of the methodology in order to instantiate the meta models at the analysis level, and then to have you know, the very first conceptual object that then will be translated into a design one, then into an implementation one, and then finally in a real deployment. Okay. And these are just a couple of snapshots related to the installation, hardware installation on our bridge, or in our department, and in the laboratories. Okay, so we used many different IoT devices of different capabilities, and we put them together using our middleware that was able, you know, to manage everything. So to manage the device level, the network level, the middleware level, the services level, and the data and ontology levels. Okay. Okay, just to conclude, in this talk, I tried to, you know, push our approach that is an agent-oriented approach for the Internet of Things. In our opinion, the approach is quite novel in the sense that it consider Internet of Things not just as a network, but as a system of systems. So it enables, in my opinion, a new wave of researchers in this direction. So the novelty of the proposal lays in different aspects, like this multi-layered agent-based architecture, based on this concept of proactive, context-aware, even cognitive smart objects that is represented by agents. So agents are, you know, proactive, context-aware, cognitive, and so on and so forth, also depending on the architectures you exploit and then you use in order to model your multi-agent systems. The Acoso middleware, you know, is and was indeed a contribution that was able to go beyond the state of the art, and sorry, maybe you got some mic open, but I'm gonna finish. So we got 3 levels of, let me just a moment. I see someone speaking. Okay, I'm gonna finish just a couple of minutes. So I also showed you a COSOMET that is, you know, a methodology that is able to fully support the development of smart objects based system, from the analysis to the implementation. Future work is around how to develop edge-based IoT systems, because, you know, edge computing, fog computing is becoming important in different domains. It came from the let's say the network domain, but now, you know, it's something that at the IoT level is being used a lot, and then we need to treat, you know, this new, let's say, this new monster as in an effective way. So we need other approaches based on, for example, simulation-driven approaches, in such a way to be able to analyze the system before the real deployment. Okay, there are many research challenges. Just one, how to put the humans in the loop in this process. Okay, this is something that we need to consider in the next generation Internet of Things system, because, you know, humans will be around for a while, still for a while, even though, you know, as I told you, 2050, there will be much more machines than humans, orders of magnitudes more. We will be 12, 13 billions, but machines will be trillions. Okay, so many orders of magnitudes more than humans. Okay, yeah, this is our Springer series. So if you got some IoT-oriented project, please keep in touch with me. Thank you a lot. Thank you very much.
So thank you very much, Giancarlo, for this really inspiring talk. And I would like to open the questions. Please just raise a hand in case you do have one. So I will take the freedom to start with the question myself. One of the last points you mentioned is data-based modeling, data mining in this field. And if you consider the Internet of Things as a as a system of systems approach, do you think one approach to go further would be in data-based modeling to use models of models to model the systems of systems?
Yeah, your question is very interesting, you know, because as I mentioned, a system of system, an IoT system of system is composed by different layers, okay? And also the data and ontologies, okay? This is a fundamental, and this is not just a layer, this is, let's say, a cross layer. So we indeed need to model data and data sources in at the different layers of which an IoT system is composed. So I agree with you that we need to take this into account. So data modeling needs to be done in a very different way with respect to traditional systems, okay? And then the data mining is fundamental, because in a small devices you can do some, you know, machine learning, lightweight machine learning, but maybe at the edge you can do heavy data mining instead of going on to the cloud, because you got even quasi real-time requirements. Okay, so you need to architecture, in my opinion, not only a new functional architecture that is very likely will be based on this concept of edge or fog computing. But then you need, in my opinion, a new database model for such systems. And going beyond even, you know, the big data lakes or such kind of infrastructure, they need to be integrated into such system of systems. So I think that in this direction we need to work much more. Yeah, much more.
Okay, thank you very much.
I actually I have a question. It's Antonio.
Okay.
Please, Antonio, go ahead.
So you mentioned at the end of your very interesting speech the fact that we are moving towards a human-in-the-loop Internet of Things. And the explosion of this Internet of Things holds huge potential for manufacturers. And manufacturers today are attracted by the promises of gains in productivity, safety, you know, and also increased insights, for example, in perspective of predictive maintenance, no? So, but as more devices are connected, manufacturers also are experiencing a deficit in skilled workers, which are able to maintain this IoT equipment. So, you know, workers are not simply able to keep up with this IoT exponential growth. So, besides the need of maybe new skilled workers that are definitely required, how can we architecture, how can we design, in your opinion, a worker-friendly IoT ecosystem? So what do we need to do in this perspective?
Yeah, thanks a lot for your question. That is, you know, very important, very important. You know, my talk was pretty general, but we are working on smart factories, specifically in China, in some of the university in which I'm also distinguished professor. So we are working a lot on these topics, smart factories. And then, of course, in smart factories, the worker is fundamental, because we still have workers, okay, human workers. Okay, maybe in the future, very likely we will not have workers anymore. We will have just robots. But now in this transition, we will have workers. So the smart factory should consider what you say. Okay, so an approach putting humans, workers in the specific terms in the loop, in my opinion, is fundamental. There are not so many approaches in this direction. Indeed, there are not so many methodologies promoting developing of IoT system. Usually, you know, everyone is used to start by scratch without any methodologies, okay, or just amending some already existing methodology. I think that this is not the correct approach, okay. So in my opinion, there is the need of what you said. There is a need of what you said, and also there should be a kind of new methodology that is able to, even in automatic way, using some augmented reality, able to empower soon, to reduce the learning curve of workers in using new kind of machines or moving around a smart factory along with you know, robots, autonomous guided vehicles, and so on and so forth. Okay, so I think that we really need a human-centered, human-in-the-loop methodology in order to build up such kind of systems.
Thank you very much. Thank you.
Thank you.
Okay, are there any further questions? So in this case, I would like to ask Antonio again to share his screen to virtually give Giancarlo our certificate of appreciation for this really great keynote. Thank you again, Giancarlo.
Thank you. Thank you very much.
Antonio, can you show, please?
Great, thanks.
Okay, great. Thank you very much. Of course, the real certificate will be transferred to you. In this case, it will be rather easy, I think, within the University of Calabria or otherwise in postal way. So thanks again.
Thank you very much.
You're welcome. And our second keynote of today's morning session, I have seen Alois Zeutel is already with us. Alois, can you please show up?
Should be here. Can you hear me?
So we can hear you already and also see you. So welcome, Alois Zeutel. Thank you very much for accepting the invitation to give a keynote today. Professor Zeutel holds his PhD in electrical engineering. The research interests are in the production area in manifold directions like adaptive production systems. Currently, Professor Zeutel is professor at the JKU for cyber-physical systems, and together with Rick Rabiser, who was giving a talk yesterday, he is heading the LIT lab for cyber-physical systems at the Johannes Kepler University of Linz. And I'm really looking forward to the talk, which is named Higgs und Dracones. So where are the dragons? Let's see. Developing software for networked productions, autonomous automation systems. Please, Alois.
Good. Let's see. I hope you see my screen now.
Yes, it's working.
I'm very happy today. Thanks, Michael, for the opportunity to that I can give this talk today. I termed it Higgs und Dracones. For those who don't know, this is coming from the ancient seafarers. I put here an old map with lots of dragons. So you see here dragons all over. And the seamen in ancient or in former times placed dragons in their maps to look to where they really didn't know what's going on here. And this is a little bit the feeling I have when I talk about software in production automation system. And this is a little bit, no, it's not a little bit, it's the theme of my talk today. So we already in the previous talk, we have heard a lot of IoT, a lot of network, a lot of new things that are coming to production. And this is a perfect introduction for me today. Thanks for that. So I would come a little bit from why we are doing this stuff and what's going on in production automation. I have here this very nice picture from Professor Koren. He is professor at the University of Michigan in Ann Arbor. And he drew this picture on showing product variety across the volume of products. So starting from manufacturing single pieces, very little volume, but high variety. So each individual product, then coming up to tailor reduce the variety a lot so that we get towards mass production, high efficient production. But Professor Koren already put the high peak of mass production 1955, which is quite some time ago. And if you see, we are going down with the volume. So mass production or mass customization is something from the 80s. And since a few years, we have something, people call it now Industry 4.0, smart manufacturing, Industry du futur. So there are many different names for that. And with that, we are somewhere here. And now people, since a few years, start to get nervous. And when you look around what's presented in papers, what's presented in industry, it feels like, we will throw in some computers, we do some artificial intelligence and robots and Internet of Things. And yeah, in German, in at least German-speaking countries, we are a lot using the word digitization for turning everything digital, and everything will be solved and everybody will be happy. And I don't feel quite happy with that, because on the other side, we have something like that. So just a year after Industry 4.0 was announced as the self-proclaimed fourth industrial revolution, Mrs. Merkel put in a very famous speech, you can find it on the internet, a talk where we said, for many of us, the internet is still a new land. So this is what's written here in German. And so internet is a new land. 2013, at the same time, a year before, we talked about Industry 4.0, cyber physical systems in production systems. And this is what I really see as problematic situation here, that especially when talking with industry, when talking with decision makers, they have very often some troubles with software. My typical question, not in a scientific conference like the one we are here today, but in other conferences or industry settings, especially talking with decision makers, management, middle management, is always, who of you is capable of programming? And this is very important, or who has programmed something in the last few years? And very little hands go up, and then I always say, now I'm happy because I can tell you everything, because you will anyhow have to believe me. And that's a problem, because what's happening with that is it leads to fear. And somehow my slide is broken. This is very bad, because you should see a different slide. Just give me a second. So you should see that slide here. I hope that's not a big problem for you, because fear is the path to the dark side. Fear leads to anger, anger leads to hate, hate leads to suffering, to speak with Yoda. And this is really the problem, because people are fearing what's going on here, and they fear stuff will break, stuff will destroy. One thing that comes along with the digital industries and with software is disruption. And I put here the very nice picture of Blockbuster. I'm not sure if any one of you know what Blockbuster is. Blockbuster was a video retail chain, a video lending chain. So you could go there and lend DVDs, or before that VHS cassettes. So for the old people here in the room. And up to now, Blockbuster wrote here, store closing this location only, because this is a few years back. So now they have only one store open left, and this store is selling merchandise, and that's all. So they were completely disrupted. They were not able to foresee what will be coming, and Amazon, Netflix, Hulu, and all these Disney Plus or whatever services took over and changed everything. And this is now something that's a general feeling that we get in industry. Are we missing something? Is software taking over? Is software eating the world? Will in the future the manufacturing industries just be the apprentices of software? Will they be just the supportive functionalities, and everything will be done in software? The good news is production is hard and complicated. And this is at least a little bit of good news. I'm not sure if you know who this man is. Some people may have seen this picture. It was on Twitter. This is Mr. Elon Musk sleeping in his office. It's 3-4 years now. And he posted that picture because they had troubles in manufacturing the Model S of Tesla. So production is not just software, but to be honest, so in the meantime, they made break even, they solved the problems of production, and now they're producing. And so software, and Tesla is one of the companies showing that software in cars is really, really important, and they change a lot in their world. On the other side, I found this very nice article on BBC World 3-4 years ago, I think, and I use that a lot nowadays because this article posted right in the beginning the question: how long did it take until electricity significantly changed production productivity, or even to phrase it a little bit more harsh, how long did it take that the electrical motor found its place in the production? And the answer may surprise you, because at the time the electrical motor was, so it's starting from the question: when the electrical motor is available, it has sufficient stability, quality, it has much higher efficiency compared to steam engines that were used before electrical motors, so the classically first industrial revolution. And still it took the electrical motors more than 50 or roughly 50 years till it got significant stronghold in production. And this is something that surprised me quite a bit, and this is something, therefore, when I talk about Industry 4.0, I'm also talking a lot about that situation. And the reason for that is something very, very interesting. It's the thing that you see here on the ceiling. Yeah, it's not only on the ceiling, but the root cause is in this belt-driven machines that you see here, and the factories and the production processes at that point in time when the electrical motor came into public domain or public use was that factories were designed to have a big steam engine in a separate powerhouse, where the steam engine was operated 24/7 and provides rotational energy to all the machines and all the equipment that needed in the factory. And machines were designed rather big, rather less trained workers, or little trained workers is, I think, the better wording, to and to operate based on that principle. So replacing one steam engine with one electrical motor, especially with a very big one, because a big steam engine has lots of horsepower, so you need a big electrical motor. This would not change anything of your production. It would not really improve your production. The only thing that it would improve was a very small margin. It was just the efficiency of the steam engine. But the productivity, the functionality of your machines, the throughput of your factory would not change. And it took 40 to 50 years until the first machines or the first ideas came up how to efficiently use the electrical motor. So, and this came up with the redesign of machines, it came up with the redesign of production processes. So it means that when we think about how technologies affect our production, our automation systems, you have to think a lot about the processes. And they pointed an additional thing out here is, if you look now at computers in business are available now 60, 70 years roughly. So in a wider use case. And in the beginning, they did just automate human tasks. So they are just quick at calculations. So they replace calculations, but it was just an performance improvement of stuff that humans did. What we see over the last 10 to 15 years is that we are now changing how we are interacting. In Web 2.0, how it was called, or social media, business-to-business interactions, lots of stuff we're changing in computers. And I will postulate now that we will see similar things in production. Otherwise, all this IoT, all this Industry 4.0 cyber-physical systems are just a very nice add-on, will maybe improve the productivity by another 2, 3, 4, 5%, but it will not be a radical change. And radical changes always are going along with also process changes. And interestingly, although the steam engine is always the icon, the figure of Industry 1.0 for the original Industrial Revolution, the Industrial Revolution as it happened would not have happened if there was not at the same time, or a little before, to be honest, a change how the manufacturing world was organized at that time. Because before this change, we had small shops, 2, 3 people at home working like on these looms, as you see here. And right before or around the introduction of the steam engine, we see the change to factory shops, to big factory shops where many people working in the same factory. Because only then, with this organizational change, also the steam engine made sense. So for me, this is a very important fact, and therefore I spend also quite some time now in my talk on that. And therefore, when we develop technologies, we also have to think about, do they apply to existing ways of production, or do we also have to rethink production? And if we have to rethink production, it may mean that it takes quite some time till it will be applied in industry, and that can be quite a long time, like with the electrical motor, 50 years. And still we are technical people, so we are talking a lot about technologies, so I want to talk also about technologies. And one thing that I've or my teams have been researching on or are researching on is a lot about making production machines more modular. So I have here this nice picture of this toy. There are few of these toys out. They are invented to teach children, sometimes very small children, to do programming, to get into the MINT studies and things like that, so to interest them for new things. And as you can see, these are cubes that you can very easily stick together and build your robots out of it. And we want to do similar things with machines. And we want to do that because we want to be our machines more adjustable to different production scenarios. So this is one of the reasons I brought the original picture where we saw that machines are changing a lot. And with that, we started to build pluggable machine components. So this was done in a research project funded by the German government. It was called OPAC. You can find it in the industry, in internet. And what we did there is we took production components, equipped them with control technology, sensors, actuators, and turned a simple mechanic component into, I would call it an infotronic component, because we have not only mechanics, electrics, and electronics, but we also have software inside, and with that, this component can be operated in a service-oriented way. So we have components that are now service providers that offer services based on their mechatronic capability. In that case, for this simple component, it would just be move out, move in, but it could also be additional things like diagnostics, like usage information and stuff like that. And the great advantage, and bringing me to software, is now that when I'm now building a machine, I can see it build of these three components. I will not consider how these components are working. I can focus on just modeling, developing the operation of my part. So this would be the operation of that unit composed of the components, and I can then easily plug them together. What is the great advantage? If we have here good service interfaces, I can easily replace one of the components. So if my product is changing and I need a different gripping device, or if I have a different customer that has a heavier product, I change maybe that component. But most probably it will not change the software I've written for my component, because the interface is hiding that. And we can, as you may imagine, aggregate that up, and we can build stuff and components together out of that. And so we can build machines out of that. So this looks very nice on slides. We did that also for a real machine, in that case from our partner Asus. And as you see here, this machine is a little bit bigger. It has a few more components. Interesting thing, companies that I'm talking with very quickly identify this is very interesting, because we build machines dedicated for certain customers, and each machine is individual. Nonetheless, we build similar machines, so the components of our machines are reused in different machines, and this can help or to get some economics of scale and increase the usability, the reuse of components. And what we did, you see here, all these green boxes are controllers. So we have here 12 to 15 controllers, and we tried to build up a machine with available industrial automation software technologies at that time. It was five years ago or something, maybe 6. And while in theory, and while the development of the components was really straightforward, and it was exactly as we envisioned, I must tell you that we completely, or not we completely, but we failed a lot. It was really, really hard in the end to get that machine up into operation. We spent a lot of time tuning, tweaking, setting everything up. And with that, we identified that the advantages of having small components with current technologies is not feasible. And that's maybe was foreseeable, but still it's important to talk about that. And what we see in industrial automation, and that's also one of the reasons I called it Higgs und Dracones, is that in industrial automation, we see a lot that people have problems with software. I have here 2 citations. They're already really old now. I find very little citable information, but every time I talk with my industry partners, when I talk with software developers, from machine builders, from plant builders, I get the same impression. And what you see here is that software is always the problem. Now, we make so nice machines, but now that we have to put software into our machines, everything is breaking down. And it feels a little bit like Heracles fighting against the Hydra. And if you know, the Hydra is a snake with many, many heads, I think 7 heads originally. But if you cut off one head, 2 new will emerge. So this is how software development feels. You fix one bug, you add a new issue, you get new 3 problems in addition, and that's all the time that you fight. Heracles was able to fight against Hydra and kill Hydra. The problem is we are all not half gods. So Heracles was a half god, so he was a little bit better than, or maybe better than us. So we need tools. And there is a very nice IEEE Computer Magazine article from 1987 from a guy, from Mr. Frederick Brooks, who pointed out there is no silver bullet. So he observed software development and software programming languages and tools and means for about 20-30 years, not 20 years at that time. And his impression in 1987 was, although software development improved, there is no tenfold or 20-fold or 100-fold increase in productivity. And that's a problem because we still have not as much software as it running on the cloud, but still our machines get more and more software. And you may think, okay, 1987, we did a lot of improvements, but in, I always forget the time, 2007 in Uppsala, at the Uppsala conference, they did a similar thing, and they brought up a panel with people you see here, like again, Mr. Brooks, Martin Fowler, very famous computer scientist, David Thomas, Ricardo Lopez, Fraser. So these are quite interesting people, and they all said it got better, but still not the magnitude that we are expecting. And so we are here in production automation systems, standing with software is the problem. And there are a few things that I wanted to point out here from that slide, and one is, and especially the second phrase is, we mastered most topics and could save up to 70% of the engineering effort. Wow, cool. So they say they improved by 70%. What makes us still problems is the software effort. And this is exactly the problem that I see, because if we look at our machines, then what we have is that you cannot treat software independently. You cannot treat software without looking at the hardware and the electronics, because our machines, our plants, our factories, in the end, it's not the software alone. And this is a key message here, which I really want to point out, is you cannot take software individually. You cannot just say with software we will heal everything. You cannot fix a bad mechanics, you cannot fix bad electrics and electronics with software. You can maybe circumvent a few problems, but in the end, it's not possible to save the world just with software in production automation system. And that's an important point. However, in the last years, we have an even further problem, is that we get something like communication. The previous talker talked a lot about IoT, which is a very important topic, but this improves even our problems in production automation. So if you would talk with the classical machine builders who is already saying mechanics was quite fine, electrics, now we have software, everything is getting worse, and now you need communication. Why should we network our machines together? And we are happy that they're working. And therefore, this is a problem. The other thing is, sometimes I call it cyber physical systems. The other thing is that if you look at the infrastructure in industrial automation is roughly based on these two paradigms. One is process control systems, the other is PLCs. So PLC stands for Programmable Logic Controller. This is the first PLC that has been introduced in 1968. And if you look at the modern PLC, it will not look much different. It has some IOs, either direct connected to your CPU, like here, or nowadays maybe via field buses, but the overall architecture, the memory layout, the programming paradigms are the same. And some people just, my animation is broken, some people just see communication as an add-on, and this is exactly the problem that we had. We were using technology based on stuff introduced in 1968. And this made us really problems. And I think the new picture that you have to draw is that you have to at least have them side by side, equally important. Some people even draw these two bigger than the others. And this makes a few things quite interesting. So, sorry, I was interrupted. Someone has not muted the mic. So some people, even you can find persons that say software and communications are getting even more important than mechanics and electrics. I still think we have to consider all of them. And this brings me to one of my key technologies that I'm researching on. I bring that here as an example, and as a researcher, I have to say I'm a little bit biased towards that technology. I'm working since my master thesis with this strange naming IEC standard. It's called IEC 61499. And since a few years, I'm even leading this standardization committee, so maybe my words here are a little bit biased. But what I wanted to point out here is what I wrote here as text, and this is my understanding of what this standard is providing you. And this standard provides you a domain-specific modeling language for distributed industrial process measurement and control system. And these words are very well chosen. A few are even highlighted, and a few things I want to talk about. First of all, it's a distributed language, or for distributed systems. So communication is a key element in that language. This is very important because, as I told you, communication is getting more and more important. So if you're looking and researching in that domain, we have heard agents, we have IoT technologies. Communication is very, very important. And therefore, if languages need to have that in the future, it cannot be just an add-on that we somehow plug to it and bolt it together. Another thing that I want to point out is domain-specific. We see that a lot in research nowadays. General purpose languages are nice. They allow you to do all the things that you need. Domain specific have the advantage that they limit you a bit, but also help you to advance, and you don't have to think about all the details because the domain specific part of the language takes care of that. So it reduces your effort, and it's very important. As we have seen on the last slide, effort is crucial, and we have a lot of effort. Everything that helps us to reduce the effort is important. So therefore, I'm pointing also a lot on domain specific. And the last point is, domain specific, and in our case, it's process measurement and control system, which is in principle, or industrial process measurement and control system, which is in principle the domain of production automation systems. And finally, the last point here is modeling language. And that's also very important for those working with different languages. Modeling languages have the idea of leveling or putting the software development on the next higher abstraction level to reduce the effort. And when especially industry thinks about modeling languages, we very often get that picture. So we have on the right, we have the UML as the unified modeling language, so that a general purpose modeling language. And the UML has the theme that you can draw very nice pictures. So like here, everything is nicely laid out, and then you have to give these nice pictures to software developers, or maybe you generate a bit of code, and then you have to manually adjust that. And what you will get is something like on the right side, everything is messed up and your code is the same as it has been before, just you have outdated pictures that someone has drawn and they're never updated. And therefore, a very important point about 1499 or any other like these languages, keep an eye on executable modeling languages. So with that, especially for 1499, at least I can say, you never go to that level, because you always stay on the design level, on the modeling language. You develop, test, debug on the modeling level. Very important, and this really reduces the effort. So you don't care about which code is behind, if there is any code behind. You treat it as your language, with that you work, and you never look behind the curtains. Another thing that I have found, which was introduced this year at the Models Conference, which was happening roughly 4 weeks ago, or maybe 5, beginning of October, is Jordi Cabot presented there a paper and wrote this very nice blog post. Is low code and model driven the same? And he posted yes, and you may have heard of low code and no code. These are buzzwords coming now. You see here a small peak in 2010, but for the last 5 years, and especially the last 2 to 3 years, it's really increasing, that you have low code replacing model driven, and the name low code for me says it better, although model has its own quite interesting points, that low code is providing us with the meaning that we would like to reduce the effort. And with that, I would like to show you, at least on one slide, how 4099 is behaving. So 4099 has a few very interesting points. The first one is you develop an application model independent of your hardware. You have components, reusable components. They are called function blocks. They are event-driven. With that, they are much nicer integratable in any IT infrastructure because you have these red lines here on top, which say when I get a signal on that line, execute me that component, and the component can notify I'm done. This was especially introduced for communication because with that events, you can now say I'm done, please send it on the network. This is much better than existing technologies. In parallel, we have a system model, which is very important when we're talking about distributed systems, that we know what devices are available. So we have here devices, in that example 5, which are connected with sensors and actuators. Very important. We are always in both directions interacting with our process or machine. And we model here the communication infrastructure, which can be utilized by our application. Very important, a very unique feature of 4099, because what you can do next is the distribution model is now, where should my application be located? This can be done manually, which is currently the preferred way of doing it, because in industrial automation, there is still quite some interest to know where stuff is running. Nonetheless, there are approaches where you can do that automatically. And especially with the information that you see in that picture, we can derive lots of information for automatically configuring the communication. And this is very important to reduce the effort of communication configuration. We have heard agent technologies, middlewares in the last talk, very important. Yeah, and yeah, this is not so important. And with that, we get somewhere to some improvements, reducing our effort, which is very important. But you don't need to believe to me. There is a very nice article of friends of mine from the Technical University of Vienna, from the Automation and Control Institute. Peter Xellmann, Martin Melik-Makumians, and Georg Schitter were researching on comparing existing PLC technology 61131 and 4099 with code metrics and comparing the effort. And when you look here, that the numbers of these metrics, that you can see that 4099 in many of these numbers is better, and in some numbers even tremendously better. If you look here at the program effort, if you look at the program difficulty, program volume, this is amazing. And this is what I meant with modeling languages reducing the effort. Especially 4099 introduced this concept of events. And this concept of events is something you need in production automation a lot. You have lots of signals like start something, stop something, tell me when you're done, tell me when you have an error. This is stuff that's happening a lot. We have lots of components interacting in production automation that way. And in classical technologies, you have to either do that with function calls, which is not always working as intended, and you have to use Boolean flags to keep this information. And this is managing these Boolean flags is a lot of effort. So you have to program that, you have to debug that, and you have to maintain that. And this is something that's then showing that number. We are not as good when it's coming to continuous processes with 4099. You see here the numbers are partly even worse. This is something that we are currently addressing in the standardization committee by introducing additional modeling elements, but also introducing tools that help you here. And this brings me to the last section of my slide. I hope I'm not too long. I think I talked a little bit too slow. It's open source technologies for industrial automation. I bring here one example, which is the Eclipse 4D project, which provides you with an open source implementation of 4099. So you get a runtime environment for executing, so that you can really use 4099 as executable models. You get the tool where you can program all this stuff. And with that, you can now have a slew of different hardware. You can connect it to your programming tool. You can program, deploy, configure, monitor, all from the tool, from the modeling. And that's what I meant with we stay on the modeling level. And as we are so network affine, we have all this IoT and cloud connectivity directly integrated. But this, please, I hope it's okay that I did one slide of advertisement. This is a very nice thing. You can Google for Eclipse 4D, I can download it by yourself. Another thing that I see very important in industrial automation, in production automation, industrial automation, industry 4.0, and all the technologies around that we now have open source technologies that can really help us to improve and work on technologies and experiment very easily. As there has been the question on the humans, I added that slide here. So originally I removed it. I hope it's fine that I take 1 minute above my time. And I found this on Twitter. And I think this very nicely summarizes what additionally goes wrong with software and industrial automation. The problem that we have is that our tools are very, very complicated. You need training, you need to know what you're doing. And therefore, and this is something that we have to get better. As it was the question with the trained workforce, we have to find ways how to make programming more intuitive, and especially the tools that we are developing are very often way too complicated. Very often they are research tools, fine, because they show, but at one point in time you also have to think about, and I think this is also very valuable research, how to make these fancy advantages applicable for the industry. And applicable for the industry has to do a lot with usability and user experience. This is especially true for multi-agent systems. Multi-agent systems, are really bad at that. They are really bad at conveying what to show to the user, how to express what they are doing to the user so that in the end the plant operator feels well. But I'm a tool developer, I'm researching on tools for industrial automation. We are not much better. So we just conducted last week a usability study on one of our tools with real-world users, and we really got partly very good feedback. I was proud of that, but the bigger part was where we sucked, and that's really, really important. And therefore here, my last slide for today is roughly promising. Are we there yet? No, but we are definitely beyond half. So we have a lot of stuff available. Software will change production automation in addition to what it already has. But one important thing, and this is mainly for industry, but also for you as researchers supporting when discussing with the industry, don't wait for all the standards to be completed. If you do that, you will never start, because software, smart manufacturing is a moving target, and we will see that changes a lot in the next years. And so you need to start early to be capable of managing the changes that will come along. And with that, I thanks again for the opportunity, and I hope we still have time for questions, and I'm looking forward to them.
So thank you very much, Alois. Of course, we have time for some questions. In order you have one, I would just like to ask you to raise a hand. Okay, Stefan Wagner, please.
Yeah, thank you, Professor Zeutl, for your very inspiring talk. I was just wondering regarding the system architecture that you presented, where you have functional blocks being distributed to the different device. This reminds me, from the software engineering point of view, reminds me of container technology and of, for example, Docker containers being distributed to devices to execute services on them. And I was wondering, do you think that technologies from software engineering, such as containers, will play here an important role regarding the system architecture that you described for manufacturing systems?
The simple answer, yes. The longer answer is container technologies. We are investigating them. I haven't talked about containers a lot today. I think I'm still sharing my slides. If you look at the architecture of our runtime environment, that you can see here, these blue boxes, and I regularly call them application containers, execution environments for component-like technologies. The problem I have with application with containers like Docker and Kubernetes or LCX is they are providing a very nice infrastructure regarding execution and shielding. They don't provide any support from the programming perspective. You can still do everything with it. So bringing a modeling language like 4099 or any other modeling language that suits you together with containers is something that I find quite interesting. And this is also something we're investigating, and I'm also looking for partners in that direction. So if you're interested in collaborating in that topic, just drop me an email. I'm very easily to be found on the internet, or maybe there is even on the ICM webpage my email address. There is only 2 Alles-Zeutels in the internet, and there is only one in Linz, so I think I'm easily to be found.
Great, thank you.
You're welcome.
Okay, are there any further questions? Rudolf Ramler, please.
Hello. I hope I can be heard.
Yeah.
Yes.
Thank you, Alice, for the great talk. It's just a follow-up question, I would say. When you talk about containers, do you also think in going into the direction of microservices or architectural things that are becoming more and more trendy in software engineering?
I'm currently supervising a second supervisor PhD thesis on microservices industrial automation. I'm just looking for the right slide. I think now it's in the other direction. I'm really pissed by the latest update of LibreOffice. I hope this will get better. So my animations are regularly broken, as you can see here. What I wanted to show, in principle, what you see here is already something similar to a microservice. It's a self-contained component. It has some kind of interfaces, and you have some, in that case, orchestration engine that can supervise and coordinate that. If it's already real microservices, what is a real microservice? This is exactly what research has to be, investigated. In our case, the point is that these are already self-contained, so the container would be the mechanical component, so it's a physical container. But this is very limiting, and I think that, especially also with the question from Mr. Wagner and yours, bringing both together and also making that where to put the software and how to isolate the software of that component, coordinating the sub-services will be definitely interesting. Another question that we are currently researching is how big these offered services are from a functionality perspective. So where do you cut? How you split your functionalities into services. This is also very important. So there's lots of opportunities for research here. Yeah.
Thanks.
Yeah, you're welcome.
Okay, another question stated by Michael Hampel.
Yeah, hello. Again, thanks for your presentation. I also have a question about when you're not using Docker or Kubernetes, how do you manage your function blocks? So how do you deploy them? How do you load balance them? Probably how do you update them? How do you monitor them? Things like this.
This is all infrastructure provided by our runtime environment, because a Docker container is for, in my opinion, or to be honest, we researched on that before containers came out. So we started around 2002. So maybe Docker does similar things, but if you look at our components are very often much smaller. So I would not compare one of our blocks with a full Docker container. So our components are software, even classes maybe. So we are at the level of classes, not a full Docker components, and therefore we need more lightweight technologies. Furthermore, we have different kind of CPUs. So we are supporting 6 or 7 different operating systems, real-time operating systems, something that I'm also very interested. I wanted to append to Mr. Wagner, also bringing combining that with real-time technologies. And so we need our own monitoring technologies. We need more lightweight monitoring technologies. We need to be smaller so that we also fit in components like that. So here we have a Cortex M3. If we are lucky, we have FreeRTOS. Sometimes we don't even have an operating system. And this is the span that we have. To be honest, newer systems mostly are bigger systems with Linux on it. So there we could even leverage more from existing infrastructure or newly developed.
Because probably if you're looking for a more lightweight alternative, you could look at WebAssembly. So that looks quite promising as an alternative for Docker. And I would have another question about your communication structure. Is this something where you have a centralized broker, or is this more peer-to-peer, or how is the communication?
The modeling system does not care. So we model just the interaction of components. Okay. And it's agnostic to I should really give my slides names. It's agnostic to the communication system. So we have then here device-specific configurations that would then represent the communication. So between these components, peer-to-peer is most efficient, but we experimented with MQTT. I would like to experiment with EDS. We experimented with ROS 1, so I would be interested in ROS 2. We do a lot with OPC-UA, because OPC-UA is for industrial automation very, very interesting, especially from the semantics. But for many things, UDP local multicast is perfectly fine.
Okay, thank you.
You're welcome.
Okay. So I do not see an additionally raised hand, and we are already pretty in time. So I would like to take the opportunity to say thank you very much again also for the question session and ask Antonio to share his screen in order to provide the virtual certificate of appreciation to Professor Zeutl. Okay, great, thanks. So thank you very much again, Alois, for this really insightful and inspiring talk. Here comes the virtual certificate, and the physical one will come in a few days per old-fashioned postal way. So thanks again. We will go into a virtual coffee break right now and restart with 4 parallel sessions at 11 a.m. Central European Time. See you then.
Thanks again. Bye.
Bye.